To you, Tamsin, and what is the true near-term commercial promise of quantum for major industry verticals? Let's find out.
Thanks so much, Tom. Yeah, so I'm Tamsin, I'm your moderator, and this session is going to look at the near-term value of quantum technologies for the major industry verticals. I think we probably need a little bit of definition here. My panelists and I have decided that near-term should be kind of roughly till the end of this decade. And instead of using the word promise as we have on the agenda, we're going to sort of just call it value, which seems a little bit clearer and a bit more near-term. As Tom mentioned, I'm a partner at Brunswick Group, the global communications firm, and yeah, formerly a writer and editor at the Economist. As we've heard from Tom and from plenty of other speakers today, there is some sort of, discussion over, whether the various pillars of quantum technology are a little bit overhyped. What's the real value here? One of my favorite stats is from Deloitte, which is that actually fewer than a dozen companies this year will use quantum computing in their day-to-day operations. Another one is that for this year, again, the total revenues from quantum software, hardware, quantum as a service probably won't exceed more than $500 million. And obviously, with the NASDAQ down 26% year to date, I think that a lot of tech, and sort of particularly frontier techs, are coming under lots of scrutiny. On the other hand, we can see the promise over time from the fact that 69% of large enterprises are looking at using quantum technology in their operations. So it's all about kind of to what degree is it really being used. So today we're going to hear about, in some detail about what these use cases really are, from a panel of experts that encompass both what I'll call the quantum industrial complex, and also from a couple of really kind of super important industry verticals. So I'd like to welcome Tony Utley of Quantinuum, Dave Fleming of Mastercard Foundry, Bob Sutor of Cold Quanta, and Dr. Thierry Botter of the European Quantum Industry Consortium. We've also got Bijoy Sagar joining us virtually from Bayer AG, which will be really interesting to hear from on the chemicals and pharma front. So with that, I'd like to kick off the discussion by asking you, Tony, firstly, you've got a kind of a new product. Quantinuum's got a new product out the end of last year, which is actually a quantum use case product, that it's commercially out there. I believe you're selling it successfully. Quantum Origin, cybersecurity. Could you tell us a little bit about it? And also, I believe that your philosophy is that don't let the enemy of don't let the best be the enemy of the good. So kind of get on and use what qubits we have and just kind of get on with it.
Sure. Yeah, I'd love to tell a little bit about it. So just as a reminder, Quantinuum is the combination of Cambridge Quantum Computing and Honeywell Quantum Solutions. So, we've been working on hardware for over a decade. We've been working on software for almost a decade. And one of the things that brought us together as a company was that you can do amazing things with these systems today. And people forget that because you can simulate today's quantum computers, they equate that to it's acting like a quantum computer, and it is not. So quantum computers today actually create superpositions, and they entangle, and they take advantage of interference. And when you do that, it turns out you can make something pretty special. And so Quantum Origin is a way to make encryption keys that are provably non-deterministic. And if you think about keys that exist today, and we talked about this post-quantum world of cryptography, the keys that are made today are not either provable or non-deterministic, which means they are themselves susceptible to what we are trying to go do as an industry in terms of making these computationally really incredible things. But you can take advantage of the quantum mechanics of quantum computers today to create these keys that now will become the foundation, the bedrock for how all encryption is done. And the keys tie to algorithms that exist today and algorithms that are going through this post-quantum work. And I think it's just a reminder that if you give incredible people access to these exceptional tools, they're going to find things to go do with them.
As opposed to kind of fixating on a particular use case that is amazing, but you just can't do it for, a decade or more.
Probably the most common thing that we end up talking to with customers is, we have a great use case, and then we all collectively agree that's 15 years away.
Could you give us an example of such
Well, I
a
mean,
use
we
case?
heard about several of them earlier today, where there are things where if you're going to do simulation for nitrogenase, that is going to take a long time. It's going to take a while before the quantum computers are going to exist at a level that you can do that. That doesn't mean that you can't think about chunking the problem into smaller bits, and that's what this is going to take. It's going to take what does this quantum computer do really well, more special than anything else, and then use it to solve that part of the problem and bring it into a bigger solution. So just by default, you're going to see this hybridization of compute, but it's really about chunking it to a size that you can tackle that with a quantum computer.
Bijoy, I'd like to bring you in here, if I may. I think that from a very large company perspective, where I believe Bayer's been running pilots and looking at partnerships and kind of really doing quite a lot of experimentation, you've got a pretty realistic view of the sort of the hype versus the reality. Could you lay out how you balance your caution and realism against kind of longer term optimism, and what are the reasons for your caution?
Yeah, thank you. First of all, I'm glad to be here. I actually agree with the previous speaker, because for things like encryption, I think that might be the way to go, because with some of the smaller factorialization problems you can actually do in what's available today. I'm in life sciences, and our problems are quite difficult, and error suppression matters, because unless you get these things at a level of accuracy, and that requires cooling problems to be solved, that requires a lot of hardware problems to be solved. So from where I sit, this is not a short-term issue, this is a longer-term issue, because those are the use cases we are looking at. But I agree that we should be taking small chunks of problems and trying to solve what we can. That's the only way to make progress, which is why I am continually investing in those kinds of things, with full understanding that the commercial value will not be harvested in life science for a number of years to come. What I worry about is the hype cycle, where people are taking these small successes, which are real, and then extrapolating them to 3 or 5 years and saying those big successes are just around the corner, which I worry about, because then you lose the value of these small successes, and people lose interest in 5 years.
And when you say long-term, Bijoy, what kind of time frame are you thinking of? Because I think it's important to pin this down a little bit.
So, I have a realistic feeling that the NISQ phase is going to last maybe another 5 years, probably more. But some of the problems we are looking in healthcare, particularly in simulations of molecular behaviors, protein folding, these things are million qubit problems. So they are probably 15, 20 years out rather than 5 to 10. And that's the realistic time frame that I'm thinking. Of course, I would happily be wrong if that happens.
Fantastic. Bob, I'd like to ask you for your sort of overall judgment on this. I mean, I think you have a very good sense of both the opportunities and the drawbacks. I mean, I think you also feel that there are players that do sort of deliberately set out to kind of come up with, estimates that aren't necessarily going to come through.
Well, I think it's always true. This word hype is very interesting. and sometimes it depends on who is speaking this. I have known scientists, for example, that if their area of science is mentioned in the commercial press, it's hype because somehow it has escaped academia, right? And it's not ready to be done that. On the other hand, there's this great extreme, I think the word extrapolation was used, where you really can't demonstrate or you can't say that you're going to have a certain performance until you actually have the computer to do it, right? And if you know so much, build the computer and show us, in fact. So a little bit of the onus of this is frankly on you, right? That is, the information is out there. Presumably you're all here to learn more about quantum computing. You're here to learn more about being educated consumers. And so through this discussion and the other discussions as well, you'll learn certain things. So the size of the problem. Well, guess what? A really hard problem requires a powerful computer. That's why it's hard, right? And things like this. So it requires either a powerful classical computer, it requires a powerful quantum computer, which typically relates to the scale and the quality of the computer. So you can find these things out. You can find out what really exists. And once again, you're not going to solve a hard problem with a really tiny quantum or classical computer, for that matter. We have supercomputers, and we don't just use our iPhones for all problems like this.
Absolutely.
So I think, therefore, at this point, in many ways, I consider this, if you will, the second generation of becoming practical quantum computing. Until recently, I was with IBM. Tremendous amount of work, and a little bit more than 6 years ago, put the first quantum computer on the cloud, which was a wonderful achievement. 6 years ago. It didn't start yesterday. So you are entering into a point where already quite a few things have been sorted out, right? So just to reiterate, I'd like you to use this conference to find out the real metrics that you should be looking at to understand for yourself what the actual progress is.
On that point about metrics, Bijoy, I might be slightly naughty and mention that you think it's expensive. You think quantum computing is expensive. Bob, I think you disagree with that. Can we talk about how much it costs and whether the investment is worthwhile?
Yeah, so I tend to see it the same way. I mean, it is expensive because we are in the early stages of what we are talking about. And a lot of the current concepts are proven on quantum simulation, on supercomputing, for example. That is really expensive. I am not seeing commercial value yet at the scale for the investment we are making. But this is not necessarily a negative comment, because anytime you're early in these kinds of experiments, you obviously are not going to see economic value right away. And so take my comments in the right spirit, in the sense that we are still, for example, if you think about artificial intelligence being something that was talked about in 1959, and we are now seeing applications which are at scale, it takes time. That does not mean we don't continue to invest and we don't try to find different ways of doing it. But right now, if you're talking about, do I see return on investment for the problems I have in front of me, I don't see it. But I say that as a person who is a fan and who is a believer in the investments.
I think I'll let the speaker of the next session talk about the cost. But let me also just, I've been talking about quantum computing for a very, very long time, and I think we've been trying to set reasonable timelines for when things would be available. So let me caution you this. If you've ever had small children, you get in the car, and they're in the back seat, and you say, this ride will take 3 hours. And after 15 minutes, they say, are we there yet? Right? And you say, no, I said it was going to take 3 hours, right? And they say, but I want to be there yet. But I want all these solutions to quantum computing because I've known about it for a while. And what's keeping you all? Well, we told you what was taking. So again, that goes into the education, but also understanding where we've come. And also, by the way, it'll happen sooner than you think.
Fantastic. That's marvelous. So I want to kind of move into the actual use cases a little bit, and just have the kind of quite a good chunk of the session talking about some of these amazing applications for quantum computing and sensing and communications. So Thierry, would you tell us, I mean, specifically on that point about expense, you run the European Quantum Industry Consortium, and one of the great advantages of that is to sort of share the cost and sort of help, collaborate and get together on that kind of thing. Can you run us through just briefly what the consortium does and sort of the sort of momentum you're seeing among your members? I think you've got over
150.
A really good number, and just give us an overview of that.
Yeah, absolutely. So QUIC, the association, came together just over a year ago in Europe by many different European actors, companies, investors, large and small and medium enterprises, looking to try and forge a very sustainable, thriving ecosystem. And the point of the association is to work on topics that are common to these many different members. So each of them have their own business focus, their own activities, their own developments, but some areas are common. And what we're talking about here today, how do we get value, where are some of these use cases, and how do we translate from the developers of quantum solutions, especially in quantum computing, to the end users, those who want to use it for either drug discovery, battery development, fertilizer products, things of that nature. What we've witnessed at QUIC is people coming together and organizations pooling resources, pooling thoughts, trying to agree on what could be some clear indicators of value added. And on that front, collectively, we've actually developed some sort of top use cases. This is the product of these many members working together, looking at different application areas and agreeing these sectors and these sort of low-scale, reduced-scale problems could be good indicators of how quantum computing is evolving and what is the road still ahead to getting to a place where now we're starting to actually be implemented commercially, getting revenues based on those quantum machines. There's more work still to be done, but I think this collaborative nature and the fact that companies don't need to go into quantum alone, especially for a company for whom quantum is not their core business, but are looking to leverage this technology. There's a real added value.
Companies,
yes, exactly. There's a real added value in working together in such a collaborative way.
Yeah, fantastic. We've got a couple of really good questions from the audience, so I'm going to ask those, and if we could try and I'll ask them, see who wants to pick it up, and let's answer fairly quickly. So the first one is from Doug. Does a future quantum computer have to worry about how far classical computing could improve in 20 years? Might that shrink the potential use cases? Tony, would you like to take that one on?
So I think we're seeing convergence of quantum hardware getting more and more sophisticated, and the amount of resources needed to do the computation shrinking. And so, I mean, like, one of the things that gets mentioned is, well, we need 1 million qubits. And then nobody follows up with, why do you need 1 million qubits for that? And because there's an assumption, and we just don't talk about some of those assumptions. Like, well, do you need 10,000 qubits to make one logical qubit? And so we are absolutely going to see the evolution of continued classical processing. That's going to happen. We're going to see it at the same time that we're advancing quantum computers, reducing the resources necessary to error correct these. But it takes thousands of hours working on these quantum computers today to make the progress. It's not a 15-minute run on a quantum computer, and all of a sudden you've solved that algorithm. It is thousands of hours spent on these very targeted use cases, or at least use case areas.
Mm-hmm. Fantastic. Dave, would you go through with us some of the key use cases for financial services?
Absolutely,
that's clearly something that Foundry has been looking at.
Absolutely, and I think for the audience, I think what you hear on this panel and many discourses around quantum is a bit of a dilemma. So if the future promise is out there, that's a future promise, that's downstream. And we know from our work that organizations that are leaders in that space will gain in security, gain in operational efficiency, and gain in product effectiveness. But that's downstream, that's a future promise. what should you do today? If you're sitting in this audience trying to, where should I go? Is there actions I can take today? And that's the action that we've taken within MasterCard Foundry, is to explore, is to discover, is to work with the software and hardware that's available in the cloud, the open source libraries that are there, to discover use cases that are relevant to your organization and really get over that knowledge gap, because the gap is quite wide. So any emerging technology has a lean-in learning curve. Quantum has quite a significant steep curve. It's still making its move from quantum physics to engineering. So there's quite a steep curve there. Through our work,
Dave, the part that you've mentioned in some of the top use cases that got me really interested was ultra-fast trading platforms and sort of optimization.
I think the ultra-fast trading platforms is probably way far out there. If you bring it into today, if you think about optimization, optimization is a financial services broad category of use cases. If you think about offer allocation, optimizing offers to individuals, how do you do that in an optimum way? Portfolio optimization, predicting the optimum mix of a portfolio. There's an awful lot of variables in there. If you think of Monte Carlo simulation, quantum computers are proving to be better at that and having nascent capabilities in that space. Or if you think of anti-money laundering, we all live in a digital 24/7 world today, and that increases the chances for money laundering. And then if you add broadening of asset classes across fiat, crypto, into other classes, that becomes a large combinatorial optimization problem that quantum computing, we believe, will be optimum at over time. So there's a lot of interesting use cases in financial services that you can get at today. You can start cutting your teeth on, building prototypes, small-scale pilots, with the promise in a 3-5 year time horizon when we get to thousands of qubits to be able to get some commercial advantage. I think at that stage, it will still be small. We'll be still on a journey. I think we all need to get on the journey, but we're going to all need a lot of patience.
Thank you.
Some of the examples you mentioned, also include machine learning, for example.
Totally.
So when we think about these use cases, they're not pure quantum use cases.
We have a great question on that, actually, so I'll read that out. What are some low-hanging fruit for NISC overlap with machine learning?
Well, I think the way I think about it is a bit like BJ said there. We're scratching the surface on AI. A lot of those use cases I mentioned today, offer allocation, liquidity optimization, we can do, but we actually do it all suboptimally. We don't really realize it, but it's all suboptimal today. There's a lot more to be taken out of that. And then AI, I think quantum AI is really a very attractive space, but I think we need to juice AI on classical machines first before we really get the benefit. So we could get feature selection from a quantum computer and optimize that process. But again, I think we still need to juice AI on quantum or classical machines before we really need to get to quantum AI. And that's a learning that we've made ourselves, is try bring it into the practical, get some value, get some business advantage, not particularly quantum advantage or quantum supremacy, get some business advantage. That's going to start your journey.
Bijoy, I'd love to hear from you on sort of pharma and chemicals. There's a lot of incredibly exciting potential for use cases there. I think that in contrast to some of Bayer's competitors, you're probably looking at these kind of use cases quite discreetly and not talking a lot about them. But please do share what you can. I think it's really about cell and gene therapy, drug discovery. Please lay out for us what you're excited by.
So I would maybe reference the previous question a little bit as well. For example, candidate identification today for drugs is an imperfect science. It takes a lot of hits and misses, and there is a lot of algorithms. So you can actually do that work today with existing supercomputers and even less than supercomputers. But quantum computing is a good potential fast charger, if you will. So even if you're not talking about quantum supremacy and all of these, let's say, high ideals, you can do a lot of early work today. And I think companies are doing that. I am actually excited about two things. One is in silico clinical trials. So clinical trials is this biggest time-consuming activity before a drug comes to market, because it takes a long time to find the patient population, target them, and then obviously put them through the trial phase. And if you can actually do in silico, and if you can actually design the clinical trial appropriately, you get a tremendous amount of value to humankind, because now you can actually bring medicines out much faster. And that doesn't need to solve the entire value chain cycle. It can be a very targeted one. Things like protein folding, when you're talking about cell and gene therapy, we're now talking about curative possibilities for diseases like Parkinson's. If you can solve it by looking at, in three-dimensional form, the molecular level interactions of the drug substances. And this might be years out, but obviously a lot of pharma companies, possibly including mine, are interested in that kind of stuff, where early steps are being taken with no understanding whether these first steps would be successful or not. And that, I think, is the realism that I would like to inject into it. We continue to do it, but we have no idea that it's going to be. My assumption is that the first several steps would be failures, and we have to learn from it before we get to somewhere what we can call early success.
Fantastic. So we've got another question from the audience, which is neatly getting me to broaden the discussion beyond just quantum computing, which is quite right. So far the discussion, and I think this is one for Thierry, if you would. So far the discussion was mostly about quantum computing. Would other use cases for quantum tech be more near future? For example, sensing, imaging, encryption. Encryption, I think we've discussed a little bit. But could you talk about, sensing, communications?
Yeah, no, that's a very relevant question. So indeed, I think quantum computing has been on a lot of thoughts and has been really the focus of a lot of communication. But other areas tend to really benefit even soon, and perhaps sooner, from quantum advances. Sensing is a great example. Already there are many solutions out there that are quantum-based, and then you can get into an argument as to what constitute quantums and what you qualify it, but a lot of optics-based sensors, a lot of very sensitive magnetic sensors, gravity sensors are coming up that are powered or at least using quantum sensitivity in order to give you information. This has already impacts. It has impacts about modeling what's around us, being able to sense what's below our feet, giving us precise timing and position, and going still beyond that. So yes, other sectors will benefit from it. And there's also the area of quantum-inspired. We heard a talk this morning from Sandbox where they talk about PQC, post-quantum cryptography. It's not fundamentally quantum, but it does look to prepare for a world where quantum is much more present, much more prevalent. And there too, there are advances happening now, standards being built in this space, in this area, and that can have an impact today for how companies are positioning themselves and orienting themselves. So I think it's a very relevant question, and to think about what you can learn from other sectors, because ultimately all of them have one thing in common, and that's the quantum information and how that information is handled. So if you can get to that, and then you can start to see the plurality of applications you have.
We had a question from the audience earlier, which I think it would be great, Tony, if you would say a couple of words on. It's sort of what's the broad impact? And so Quantinuum obviously is one of the largest quantum firms out there. You're one of the most global. You've got a really kind of large quantum native workforce. So the question is, what's the overall impact on society of quantum technology? It's a big question, but if you could kind of share a couple of impressionistic thoughts.
Yeah, I think some of the earlier talks had it right in terms of the future that has quantum computing at full scale. We have about 450 people right now, which, when you think about the scarce resources that exist in quantum computing, the human resource is the scarcest. And we're going after these just incredible, mind-blowing things, but it's going to take a while to get there. So the new drug trials that are completely designed through a quantum computer versus I care about that particular atom in this molecule. How does that bind to the target area. Can I do that more quickly? And that's where we're starting to see some of just the brilliant changes that are going on in quantum computing right now, is target those areas where you're going to see change that happens in next 2 to 3 years, and things like quantum natural language processing that it might take a decade, but we can already use toolkits now to prepare us for a decade from now, where you have meaning-aware machines that can listen to you and understand what you're actually meaning as you say these things. So it covers that range of possibility.
Wow, that's something that would be extraordinary.
If I could also just insert, we've talked a lot about the future, but it's not as if a lot of these quantum things haven't been going on for a while. So you mentioned sensing. We've been doing that for 15 years, right? We've been doing other types of sensing. We're going to be able to produce much better, more accurate atomic clocks that will have lots of implications for financial services, high-speed trading networks, for example. But it's based on technology that works, and in fact, you can buy today, right? So quantum isn't just this new thing that's only invented for quantum computing. So bear that in mind. We're in the midst of quantum becoming much, much more part of our lives. Computing is one part of it. I think it will become much, much more pervasive.
Bob, I have a follow-up question. It's a pretty technical one for you from Einar Magnusson. Can you share an example of a problem that has been successfully broken down into chunks manageable for NISQ devices that brought us closer to quantum advantage? Anyone know the answer to that? Or have an example, rather?
Once again, once again, I'm thinking of proposing to a friend and the next speaker that perhaps he covers that. There is no quantum computer in the world right this second, okay, that has solved problems that can't otherwise be done classically. Right? There's the proof of quantum supremacy. That was a particular type of thing. Here I'm talking about practical business problems, if you will. So there are techniques to take what look like larger problems and break them down to smaller pieces, but you're not done. You then have to glue them back together, right? And that can take a lot of computation. And one point that's really essential to mention here is it's not like quantum computing is going to take over classical computing. The future is both of them. You can't do quantum computing without classical computing. We just have to get smarter about how we integrate them. It's not a hybrid, it's the way it works, right? Just like a GPU, right? It's not a hybrid, it's just the way we do computing. So we look at this larger computing model, one part of which is quantum. So where I was going with your point with your use cases, so AI, machine learning, you've got to have that for parts of many solutions. And then yes, there's a quantum computation aspect, but it's all integrated.
And the today piece of this is, it's not new problems, it's existing problems, but you need to scale them down. Scale them down to work with them on the quantum computer, scale down the amount of data, and then keep pace with the development of the infrastructure and the hardware as you can scale them up. The lead-in time for this is long. Now is time for action. Do the experimentation, scale down your problems, and then work over time and keep pace with the infrastructure as it's delivered.
So unfortunately, we've only got a minute and a half left, and we've got a really important bit at the end of this subject, which is cross-industry collaboration. Could I hear from Bijoy on, from Bayer's point of view, from your point of view, how important is collaboration? How much of it is going on? And then also, so I'm afraid that would be about 30 seconds to comment. And then just lastly from Thierry on the same thing, since you've got that perspective.
No, we are completely believers of the fact that you can't do it alone. And for also the reason that you don't have enough technical knowledge in the field, that you have to pull it. So we are collaborating with larger companies who are experts in this area. We're collaborating with research universities. Clearly, that's the strategy going forward. Doing it alone for us would be years and years ahead, and not something that we are looking at right now.
Brilliant. Thierry, last thoughts on that?
Absolutely agree. And I think this is at the very heart of the association, Quake, how we operate. the topic is complex. The way to get to commercialization and value creation is going to be a long one, and it's going to require many different bits of knowledge being pooled together. And even for the manufacturers of quantum system, they're drawing in from a very capable set of new talents coming on the market, but even there, having the handshake to research will be important. And ultimately, we have to remember the challenge is against nature and the very fundamentals of physics in terms of making this happen. So pooling those resources and working together is essential.
Fantastic. Thank you so much. I think that the variety of what we covered there, I think it would be almost an insult to try and boil it down into 3 simple themes. So I hope you found it interesting. Thank you very much to the audience, and fantastic questions, and thank you to our panelists.
Thank you.
Thank you.
Thank you.